Okay, welcome to section 5.7, special cases. There are 3 special cases we're going to talk about when it comes to factoring. The thing is, they're not that special. They're just kind of interesting cases. They are very convenient if you remember them, but they kind of follow the same idea as the last video where we're just undoing multiplication. Okay, the first case is called difference of squares. Many people remember this one because it's pretty straightforward. You have the difference, or the subtraction, of 2 squares. So if you have 2 squares being subtracted, this is what it becomes when it factors. So let's take a look at that with an actual number example. Here I have t squared, which is a square, and I have 36, which is 6 and 6. Now yes, 36 has other factors, but I'm kind of going for the convenient case here. Okay. You'll also notice there's no middle term. There's no middle term with this. It is a 0t, and that isn't a coincidence. Okay, I'm going to take a lot of time on this first one. If I were to rewrite this as a trinomial, it would look like this, and it would be the same thing. Okay, so we're going to actually pretend we're working with this one, okay, and we're going to pretend that, well, not pretend, we're actually going to just factor this the same way we did any other trinomial. So what multiplies to t squared? T and t. What multiplies to 36? 6 and 6. Okay, and yes, again, there are other factors of 36, but I know that this is a special case, so I'm going to go with the square one right now. Okay, now when I set this up, it's a negative 36, and so in order to get 0, I'm going to have to do positive and negative, right? That's going to give me t squared minus 6t plus 6t and minus 36. So if I were to multiply that back out, minus 6t plus 6t minus 36, we could see that we get a cancellation in the middle, and that's how we ended up with 0t. Okay, and so this would be our factored form. Now, because this is what we consider a special case, right, quote unquote, we get that cancellation every single time. Because of that, if I see a binomial and I'm thinking factoring, and I say, hey, wait a minute, that's a square. Those are all sorts of squares. What happened there, right? Again, it's not steps. It's not in difference of squares. You set this up and this goes there, blah, blah, blah. No, it's I'm realizing that the middle has canceled. The middle is not there. It's gone away. And because of that little fact and the fact that they are squares, I can quickly factor this into t plus 6t minus 6. But notice that the rules of this game have not changed. Okay, the rules of this logic are the exact same as the last section. I am merely undoing the multiplication. It's just an interesting note that the middle has canceled. Okay, so here if I look at this one, I say, hey, wait a minute. There's no middle term. That's interesting. Let me take a look on the ends here. Are they squares? Because if they were squares, then that means things have canceled in the middle. Now if they're not squares, then that means that's not what's happened. Right, hence the name difference of squares. But if I see that, if I say, hey, wait a minute, that's a binomial, are there squares? I look at there, and I say, oh my gosh, there are squares. This is 2 squared, and this is a squared, and this is 8 squared. So notice the same writings as last section, right, same idea. But now that I've seen that those are squares, and they're in fact being subtracted, and there's no middle term, I know that what must have happened was that I had this. So I can do another logical, almost a shortcut. Okay, now in this one, this is not the best factor form because you can see there's still GCFs here, right? So we could go we should go one step farther and take out a 2 from each of these. And we would get a total of 4, a plus 4, a minus 4. We could have also taken out the 4 from the beginning. We would have gotten the same answer. But the point still stands. There were squares on the end, and so it factored into this kind of special case. All right, let's try another one. Again, I'm noticing no term in the middle. Interesting, that means maybe something canceled, but only if there are squares on the outside and it's being subtracted in the middle. Are there squares on the outside? 16, 49, m squared, p squared. Yep, that's all squaring of everything. Here I have 4m being squared. Here I have 7p being squared. Ah, it must have been the case that it was 4m plus 7p. And 4m minus 7p. That had to have been the factor form. Now, if you don't believe me, multiply it back out. 16m squared, that would be negative 28mp, positive 28mp, there's the thing that cancels, and negative 49p squared. which is what we began with. All right, so this case, not too bad, right? Okay, no middle term. I'm noticing on this one also no middle term, but no squares. 2 is not a square, 18 is not a perfect square. They both have 2 in them though. So let me start by taking that out. Ah, now I see squares. So it's not always like an obvious, right? But you want to always double check. That's why GCF, pardon me, was the first one we were taught. It's probably the most powerful, if not the most useful, right? We want to double check things. Here, this is also difference of squares. X minus 3 and x plus 3. With this one, there is a special note. With this case, people like to think about this as, well, there's 2 x's here and there's 2 3's here, so one of them goes over here, one of them goes here, and one of them goes here, and one of them goes here. So they start to like divide it up, and that's just going to lead you down the rabbit hole. Okay, it's going to be a bad mess for you. You don't want to do that. Do not think of this as you're taking an x and putting it over here, and you're taking one of the 3's and putting it over there. Okay, that's not what's happening. We are still going with the logic that 3 times 3 will be the 9 place, right? That will be the last one. But we are also saying that these 2 middle guys will cancel each other. So there's still 4 things being multiplied here. You should always, always, always think of factoring as undoing multiplication, not as dividing things out. Okay, you're not distributing things to places. Okay, in fact, you're doing the opposite. You're undistributing things. Okay, so that's just a little word of caution. I don't want anyone trying to remember this as dividing it out, because then we get to the next one and you're like, what the heck are you talking about? Okay, for x to the 4th minus 81 may not look like difference of squares, but again, maybe they're hidden. Here I have x squared squared, and 81 is 9 squared. So maybe I do. Here I have x squared minus 9 and x squared plus 9. Okay, but I'm not quite done yet, because I'm noticing another couple set of squares, right? Here I have x plus 3 and x minus 3. And I really, really, really want to do that for the other one, but it's not a difference, right? I have to remember that this multiplication only comes about with a minus in there, right? I don't have this cancellation if one of them is not negative, and that last one should be negative 9, not positive 9. So this one stays the same. It cannot be factored yet. We do not know how to undo that yet. So this would be the final form for that guy. Okay, so that's the first special case. Second special case you may have also heard of different name for. The first name is perfect square trinomials. You may also know it as trinomial squares. Whoop-de-doo. But kind of along the same lines. This one, we get a square out of it. So it's kind of not as obvious that it could be one. We're going to kind of approach this the same way. We're going to look at just general trinomials. So it's a trinomial, right? That's cool. I'm noticing some squares on the end. Okay, but this term isn't missing in the middle, so something else happens. Has to be happening. 3 times 3, 3m times 3m, and 4 and 4. Those are squares. Now in the middle, if I multiply those like it was any other thing, I'm noticing I'm getting 2 of the same thing. Not canceling things, not 6 and negative 6, but I'm getting 12 and 12. I'm getting double, okay? I'm getting twice as much. So if I notice it's twice as much, well then what I can get is 2 of the same thing. Or something squared, hence perfect square trinomials. Okay, again, special case. Not necessarily something we have to recognize in these ones, but I don't really want to go through 1 and 9 and 2 and 8 and see if those options work, because I see that the 12 and 12, the 12m, 12m here, that I'm going to get out of both of these, those are exactly the same. And so when I add them together, I get 24, right? 24 is double that. If you want to read this thing up here, notice it has a 2 in there, right? That just means you're going to get 2 of them. You're going to get 2 of the thing in the middle, okay? All right, let's try another one. Works with minus as well. So 144, that is also a square. I could get 12p and 12p. There are other things I could do, but I'm noticing it's a square, so I'm going to kind of maybe try that first, just in case. Here's 5 and 5. That's also a square. That's super convenient for me. I hope this works out. Now, what is 12 times 5? Do I actually get a double here? Remember, if this doesn't work, that's okay. It's fine. But 12 and 5 would be 60 and 60 p. And double, that is 120. Now notice it's a negative. So I'm going to have these 5s be negative so that these will be negative, so we get negative 120. But it's the same idea. 12p minus 5 times itself has given me that double in the middle. Also known as 12p minus 5 squared if you're lazy like me and don't like to write it twice. Okay, cool. So now is this going to work with all trinomials? Let's see. Here I've got 2 and 2. Here's 7n and 7n. This is one of those ones that has multiple variables, right? So let's see, does it work with this one? It should. It should work with this. It doesn't matter the variables. We have very little conversation about the variables. So let's look at that. Do I get double? Let's see, that would be 14 and 14. It does not equal 20 when I add those together. It equals 28. So this is not the factored form. Now that doesn't mean I can't factor this. Okay, it doesn't mean I can't factor this, except if I were to check 1 and 4 and 1 and 49, none of those combinations equal as well. So this was what we call prime. The special case did not work here. Okay, and that's okay. It's called a special case for a reason. It's special. It just happens to come about. All right, so that's perfect square trinomials. That's the second case. The last one is called difference of cubes. This isn't really one we've been working with because we haven't been dealing with cubes a lot. But it is another way. It's kind of along the same lines as difference of squares. It's a sum or difference. So this one actually works with both addition and subtraction, but only with cubes. It's a lot more string, but it's the same idea. Okay, you have a lot more things that just cancel. So in difference of squares, you had the 6t and the minus 6t canceling. Here you're going to have a couple more things canceling. So if I were to look at this one, I'm just going to follow the pattern right now. I'm just going to tell you what the factored form is because it's easier to see backwards. Okay, this one you may just want to memorize, to be honest. But m minus 2, m squared minus 2m plus 4, nope, 4m plus 4. Okay, so that's the factored form. Now, how did I do that? Well, m cubed, that's a cube, because it's m cubed. 2 is a cubed, no, sorry, 8 is a cubed of 2. 2 cubed, oh, my stylus does not like 2's. Okay, 2 cubed is 8. So this is a difference of 2 cubes, much like t squared minus 36 is a difference of 2 squares. Okay, so here is a difference of 2 cubes. For the first part, notice it's lopsided, right? We end up with a binomial and a trinomial. Okay, here I took off all the cube parts and dialed everything back to a single. So 1m instead of m cubed and 1, 2 instead of 2 cubed, right? These are the squares of those, m squared and 2 squared. And then I knew I did it wrong. Sorry. This should have just been a 2. And then this is 2 times m. So this is the 2 of them multiplied together. So singles, squares, and multiply. Singles, squares, and multiply. Why? Why the heck is this the factored form? Let me show you why. Because of the multiplication. Right? This is the undoing of the multiplication. So if I were to multiply this whole thing out, I would start by multiplying the m to everything. M cubed plus 2m squared plus 4m. And then I would multiply the negative 2 to everything. Negative 2m squared minus 4m minus 8. Now take a look at that and tell me what you see. I see a cancellation and a cancellation. The entire middle drops out, just like the 6t and the minus 6t. And it's interesting. It's an interesting case that is the middle. So we go all the way back to a binomial with this case. It only happens when you have singles, squares, and multiplication. Just like the difference of squares only happens when you have squares and a cancellation of middle terms. Right? Or you have plus or minus the same thing. Right? Or the perfect square trinomial only happens when you have double in the middle. Okay, let's try another one. So, do I have cubes? Yes, and this would be a cube of 3. Let's try just doing that now. Notice this one is addition. It actually works for both. I'm going to show you that it works for this one too, but let's just factor it out first. So r plus 3, r squared, and 3 squared is 9, and 3 times r would be 3r. Now as for the signs, notice this one matches, this one matches, and then it's always plus because that's a square, right? Squares are always positive. And then you got to have a negative somewhere, so this one has to have a negative here. Notice this one already had a negative, and so they were both positive. Okay, now prove it, Miss K. Prove that that weird, crazy thing you just did, that you just created out of the ether, actually does multiply back to this. So if I, again, multiply the r, I get r cubed minus 3r squared plus 9r. Now if I multiply the 3 in, I get 3r squared minus 9r plus 27. And again, what we see, cancellation here, cancellation there, I'm just left with the ends. So same idea. You don't have to prove it every single time, I just wanted you to see that it actually does work. Alright, let's go through these last ones now. Some cubes here, definitely some cubes. So I've got 3 and 2. If you're not as familiar with your cubes, that's okay, but you're going to want to practice. If you don't know how to do a cubed root in the calculator, for the love of everyone, please don't use the iPhone for the cubed root or something. Go grab like a TI-83. And if you don't know how to do that, I will gladly show you. Just come see me real fast, okay? I'm not ever going to do the cubed root of anything on the iPhone. It's just a headache. Okay, so 3x minus 2y. Then I'm going to square those. 9x squared and 4y squared. Okay, and then in the middle I'll do the multiplication, so 6x and y. Since they're both minus, it's plus. There's your factored form. Do I need to logic my way to that? You could. You definitely could logic your way to that. But the logic is kind of that double check that I showed you. You're kind of letting other people do the logic for you here and then just using it. I know that's probably pretty bad because what's the point of this class is to learn logic skills. But here, it's also okay to build on other people, right? We don't need to rediscover the wheel every single time. So we're just using a fact that we already know. Okay, 3 and 5 cubes, so we're good here. So we would have 3y plus 5, and let's see, 3, so 9y squared, and 25. And because this is positive, I have to do a minus, multiply 15y. There's my factored form. Singles, squares, multiplication. Then I just got to make sure the signs are right. All right, moving right along. Okay, this would be 10 and 3. Those are both cubes. And again, I recommend that you pause the video, try these out on your own, then go back and see, like, did you get them right? Okay, watching me do 8 of them, it's not helpful to you. But you're not in class, and I'm not going to sit here for recording my silence for 15 minutes while you do a couple problems, okay? So pause the video, try them out, see what you get. 10k minus 3n, that would be 100k squared and 9n squared. And then their multiplication would be 30 kn, add. All right, there's that one. Here, interesting, I have an s to the 6th on the end here, but I've seen this thing before, right? We had an x to the 4th. This is the same idea. So here, this is 5t cubed. This is 6s squared cubed. So this whole thing has been cubed. So I'm just going to treat that like it was 5 and 6. So here, that would be 5t plus 6s squared are my singles. And then 25t squared, 1 squared, 36, but then s squared squared would be s to the 4th. Now if you didn't get chapter 5.1, that's going to give you a migraine. So go back to 5.1 and see about the rules, or better yet, don't waste your time searching around a bunch of videos, come see me in person. Come see me in person about that one. That one threw you off. Their multiplication of 5 and 6 is 30, t s squared, plus and minus. There we go. Alright, next one. Doesn't look like it's a cube. 3 is a 3, not a cube. But let me try maybe a GCF first. You never know. Could work, could not. Let's see, 192. Is that even divisible by 3? Hey, look at that, it is. And I do believe 64 is not only a square, but a cube. It is a cube of 4. Now be careful, we're dealing with cubes here. While it would be super nice to write x plus 4, x minus 4, that's not the pattern, right? That's not what, if I multiply those two together, I don't get x cubed plus 64. So keep the 3 out. Instead, x plus 4, x squared, 4 squared is 16. And then 4 and x, that's a plus, so minus and plus. All right, looking good. Okay, another idea here about substitution, right? This is a cube. It's just a cube of a polynomial, not a cube of a variable or a cube of a number. So this is a cube. So I can split it up. Okay, so this would be x plus 2 plus t. Okay. Over here, I have x plus 2 squared minus x plus 2 times t plus t squared. Now one could argue, let's go ahead and multiply those out, get a better, visual representation, but if we do, aren't we multiplying, not factoring? Shouldn't we be undoing multiplication in factoring? So by leaving it as an x plus 2 squared and an x plus 2 times t, isn't that essentially factoring? So we will definitely want to leave that as a factoring. Okay. Okay. And then the last one, we have 2 squareds. That's awesome. We have squareds. But this is kind of a trick problem. We don't have a sum of squares. There's no sum of squares. There's sum of cubes. These aren't cubes. And so this is, we could take out a 4. Take out a 4. We'd have 4, no we wouldn't. We'd have 16x squared plus 25. And we have 4 and 4 and 5 and 5. So, yes. And that's it. I mean, even then, we still have squareds, and it's so tempting to want to make that 4x plus 5 and 4x minus 5, but that is an addition in the middle. And so it would not result, if we did multiply to back, we would not get I. We would not get that problem there. So this would be our factored form. Okay, special cases, 3 of them. Difference of cubes, perfect square trinomials, or trinomial squares. Difference of squares. Know them, love them, use them. And if you have any questions, please come see me.